I want to tell you about something that happened today with 3i Atlas, and honestly, it's the kind of thing that makes you sit back and realize we're watching something genuinely unusual unfold in real time. So NASA was going through the daily data for this interstellar comet, right? The same routine they do every single day. Telescopes all over the world send in their observations, spacecraft add their measurements, and everything gets fed into these incredibly precise orbit calculations. It's the kind of work that usually produces numbers so consistent, so predictable, that you could set your watch by them. Except today. Those numbers didn't line up the way they were supposed to, and I don't mean in some tiny, negligible way that you could brush off as instrumental noise or atmospheric distortion. I mean in a way that made the tracking team stop, recheck everything, and then realize that 3i Atlas had actually changed its trajectory again. Before we continue, if this has your attention, you can subscribe, turn on notifications, and hit like anytime. And for the best viewing, switch to full screen and enjoy what's coming next. Now, before you think I'm being dramatic, let me explain what I mean by that. Obviously, comets move. That's what they do. They orbit, they follow predictable paths based on gravity and physics, and all the fundamental laws that govern how objects travel through space. We're really good at calculating those paths. Give us enough observations, and we can tell you where a comet will be months or even years from now, down to incredibly small margins of error. But here's the thing about 3i Atlas. It's not just following gravity anymore. It hasn't been for a while now. It's actively pushing itself in ways that keep surprising us. And today was another one of those moments where the data came in and everyone had to acknowledge that this object is doing something our models didn't fully account for. Let me walk you through exactly what happened, because the details matter here. Every observatory that tracks 3i Atlas sends in position data. These are incredibly precise measurements, just dots on the sky with exact timestamps attached to them. You take all those dots, plug them into an orbit solver, let the software calculate where gravity should be pulling the comet, and add in a small correction for outgassing, the gas and dust jets that comets naturally produce as they warm up near the sun. And if your model is accurate, the differences between where you predicted the comet would be and where it actually is should be microscopic. We're talking fractions of an arcsecond, tiny discrepancies that are mostly just measurement uncertainty. Yesterday, those differences were well within normal limits. Everything looked good. The comet was right where it was supposed to be, give or take the usual observational scatter. Today, when the new measurements came in and got run through the tracking software, something changed. The residuals, those little misses between prediction and observation, weren't scattered randomly anymore. They were biased, systematically offset in one particular direction. The comet was consistently showing up a little bit to one side of where the model said it should be. Now, the first thing you do when you see something like that is assume it's an error on your end. Maybe the reference stars used for positioning were off. Maybe there was a timing issue with one of the Maybe something in the calibration wasn't quite right. These things happen. Astronomical observations are incredibly precise, but they're not infallible. That's so the teams went through everything. They pulled data from multiple sites, different telescopes, different cameras, different parts of the world, northern hemisphere, southern hemisphere, the works. If this was just one telescope having a bad night, the others would show the comet in the right place, but they didn't. Every single observation showed the same offset, same direction, same magnitude. The comet was consistently displaced from its predicted position, and then, just to make absolutely sure this wasn't some systematic error affecting all the ground-based telescopes, they checked the spacecraft data. There's a solar observatory that's been quietly tracking 3i Atlas in its coronagraph images, and it had just sent in an updated position measurement. This is an entirely different type of observation, different instrument, different method completely independent of the ground stations, and it showed the exact same thing. The comet was off the predicted track in the same direction. At that point, there was no getting around it. This wasn't an observational error. This wasn't bad data. The comet had genuinely moved, not just forward along its orbit, which of course it's constantly doing, but laterally across its predicted path. It had shifted to one side, to get the orbital model to fit the new observations. The teams had to go back and adjust what are called the non-gravitational parameters. These are the parts of the equation that account for all the little pushes and shoves that come from the comet's own activity. Every time a jet of gas bursts out from the surface, it acts like a tiny rocket thruster, giving the comet a little push. Usually, most of that push is in the direction the comet is already moving, either speeding it up slightly or slowing it down slightly. That's the normal behavior we see with most comets, but yesterday's orbital solution was based on the assumption that most of the non-gravitational force was acting along the direction of motion. Today's data says that's not enough anymore. To make the model work, they had to increase the sideways component of that force significantly. What that means, in plain terms, is that 3I Atlas is now being pushed more strongly to one side than it was before. The pattern of the jets and vents spewing material into space has changed in a way that's altering the comet's trajectory in real time. And here's where it gets really interesting. While the orbit specialists were working on that problem, the imaging teams were doing their own analysis. They've been taking deep exposure photographs of the comet, using long integration times to capture as much detail as possible in the coma and tail. They stack multiple images together to bring out faint structures, and then they compare those stacked images from day to day to see how things are evolving. When they compared yesterday's image to today's, they saw something that perfectly matched what the orbital data was telling them. The tail hasn't dramatically swung around or anything like that. On large scales, it still points generally away from the sun, which is exactly what you'd expect. Solar radiation and the solar wind push comet tails away from the sun. That's basic comet physics. But when you zoom in close to the nucleus, into the inner coma, the region just a few tens of thousands of kilometers from the comet's core, that's where you see the change. The whole structure is skewed. The brightest part of the inner coma, the densest concentration of gas and dust, is offset in the same direction as that orbital drift. The main jet, instead of pointing directly away from the sun, like you'd normally expect, is canted off at an angle. Think of it this way. Yesterday, if you looked at the comet's activity, it was like looking at the exhaust plume coming off the back of a car driving down a straight road. Pretty much what you'd expect, a plume pointing backward along the direction of motion. Today, it looks like that exhaust is being blown sideways, or like someone physically turned the tailpipe. Either way, the net result is the same. The push the comet is experiencing from its own outgassing is no longer aligned with its direction of travel. It's pushing the comet off to one side. And there's more. The rotation data has picked up something odd as well. Astronomers measure how a comet's brightness changes as it spins. Comets aren't perfect spheres. They have irregular shapes. They have brighter and darker patches on their surfaces. And as they rotate, those variations cause the overall brightness to fluctuate in a predictable pattern. We call this the light curve. The rotation period of 3I Atlas hasn't jumped dramatically like it did on some previous days when we saw those sudden changes. But the shape of the light curve has definitely shifted. Where before you'd see one strong brightness peak per rotation, and then a softer, less pronounced secondary peak. Now that secondary peak is becoming sharper, more defined, and it's arriving earlier in the rotation cycle. That's a telltale sign. It means an event that was previously weak, or maybe even dormant, has become more active. It's now contributing more strongly to the overall brightness and to the total out. A different part of the comet's surface has woken up. So when you put all of this together, you get a really clear picture. The orbital calculations say the comet is being pushed more sideways than before. The images show the inner coma leaning in that same sideways direction. The light curve indicates that a different combination of events has become active. Everything is consistent. Everything points to the same conclusion. 3I Atlas has reconfigured itself. Its engine, if you want to think of it that way, has changed. And that change is now actively altering the path the comet takes through our solar system. That's so the obvious question is, why? What happened inside this object to cause this change? There are a few possibilities, and honestly, all of them are pretty fascinating. One idea is that the heat from the sun, from the comet's close approach a while back, has finally penetrated deep enough to reach a reservoir of volatile ices that was buried beneath the surface. Not just any reservoir, but one that's offset from the center. Not symmetrically placed, maybe sitting under a particularly thick or tough patch of crust. When that pocket of ice finally got hot enough, it didn't just gently leak out. It punched through, blew off the overlying crust, and opened up a new major vent. Now you've got this powerful jet firing from a part of the nucleus that wasn't doing much before. And because it's offset, because it's not firing from the center or in a balanced way, it's adding a significant sideways component to all the existing forces. Another possibility has to do with the comet's rotation. Every asymmetric jet, every plume of gas shooting out from one side of the comet, exerts a torque. It's trying to twist the comet. Most of the time, these torques roughly cancel out, or at least they're small enough that the rotation stays pretty stable. But over thousands and thousands of rotations, if those torques are even slightly unbalanced, they can gradually change the orientation of the spin axis. They can tilt it, shift it by a few degrees. And if that's happened, if the nucleus has rolled even slightly, then parts of the surface that used to be aimed one direction are now aimed differently. Vents that were previously pointing mostly backward, acting like a tailwind, could now be pointing sideways. You don't need any dramatic new explosion or outburst. Just a gradual reorientation of the whole object changes where the forces are directed. Then there's the third idea. And this one is honestly a bit more unsettling. The more data we get on 3I Atlas, the more it's looking like this thing is built in layers, like an onion. Different layers, with different compositions, different mechanical strengths, different networks of cracks and fissures. As the comet warms up and those layers get activated one by one from the outside in, the behavior doesn't just smoothly ramp up and down. It fundamentally new vents open, old ones get choked off or collapsed. Stress patterns shift as material sublimates away and the structural integrity changes. The net effect is that the comet keeps adjusting, keeps changing how it interacts with the space around it, how it pushes against the forces acting on it, even as it's moving away from the sun now, heading back out into the cold. It's still evolving, still reorganizing itself. And that's why today's observation matters so much. This isn't about danger to Earth. Let me be really clear about that. This trajectory shift doesn't change the fact that 3I Atlas is safely passing through our solar system on a path that poses no threat whatsoever to our planet. This isn't about impact, risk, or anything like that. This is about what's happening to the comet itself, about the stability of this object, because when you look at comets from our own solar system that go through this kind of prolonged, uneven forcing, this kind of continuous reconfiguration, they don't all make it. The ones that survive, the ones that stay intact, are the ones that eventually find some kind of balance. The spin stabilizes, a dominant set of vents establishes itself. The non-gravitational forces settle into a predictable pattern. The comet reaches a new equilibrium and maintains it. The ones that don't find that balance keep changing. They keep shifting how they move, how they vent, how they spin, until eventually the structure can't keep up with all those stresses. The nucleus cracks. It splits into multiple pieces, or it just gradually dissolves into a long stream of fragments that slowly spread out along the orbit. Now, 3I Atlas isn't there yet. There's no confirmed debris trail behind it. We haven't spotted a secondary nucleus breaking away. There hasn't been any catastrophic brightening event that would indicate a major structural failure. By all accounts, it's still one coherent object, but the fact that NASA has to keep updating the trajectory, not because we discovered some new gravitational influence we didn't know about, not because we made an error in the initial calculations, but simply because the comet itself keeps changing the way it pushes against gravity. That tells you something really fundamental and really important. This interstellar visitor is still in the middle of its own story. We caught it at a time when it's actively evolving, actively responding to the stresses of passing through the inner solar system, and we don't know yet how that story ends. If the next batch of data shows that this sideways push is leveling off, if the inner coma holds its new orientation and stops shifting, if the rotation signature settles down into a stable pattern, then maybe this is it. Maybe this is the last major adjustment, the final configuration that 3I Atlas will carry with it as it leaves our solar system and heads back out into interstellar space. But if instead, the offset keeps growing, if the jets keep leaning further and further, if the light curve keeps changing and reshaping itself, then what we saw today is just one frame in a longer sequence of an object that's trying, and maybe failing, to hold itself together under all that internal change and stress. Either way, we're not just tracking a dot moving across the sky. We're watching this object make decisions, in a sense physical decisions about how to respond to heat, to stress, to the loss of material, to changes in rotation, day by day, observation by observation. 3I Atlas is figuring out, in the mechanical sense, how it's going to leave our solar system, whether it leaves as one intact nucleus or as a scattered stream of fragments, whether it leaves spinning fast or slow, whether it leaves quietly or with one final dramatic outburst. That's what makes this so compelling. Every new position measurement isn't just another data point. It's a clue about what's happening inside an object that traveled for who knows how many thousands or millions of years through the empty space between stars, only to wake up and start falling apart just as it passed through our little corner of the galaxy dot. And the thing is, we almost never get to see this. Most interstellar objects zip through too fast, or they stay too far out, or we discover them too late. But 3I Atlas came close enough, stayed bright enough, and we caught it at exactly the right time to watch this whole process unfold, to see an interstellar comet not just passing by, but actively changing, actively struggling with the forces it's experiencing. So when I say it moved again, when I say NASA caught something new today, I'm not talking about some abstract orbital mechanics problem. I'm talking about watching a real object, a visitor from somewhere else, dealing with real physical stresses and real time making adjustments, shifting its path, reconfiguring itself, all while we track every single move. That's not something that happens every day. That's not routine astronomy. That's being present for something genuinely unusual, something that might only come along once in a generation or more. And it's still happening. It's not over. Every day brings new data, and every batch of new data has the potential to show us something we didn't expect. So that's where we are with 3I Atlas. It moved again. It pushed itself sideways in a way our models didn't predict. And now we wait to see what it does next. Because with this object, we genuinely don't know. We can make educated guesses. We can run simulations. But at the end of the day, 3I Atlas is going to do what it's going to do. And all we can do is watch, measure, and try to understand what we're seeing. And honestly, that's exactly how science should feel, not having all the answers figured out ahead of time, not being able to perfectly predict everything, actually being surprised by nature, and then working to understand why you were surprised. That's when you know you're learning something real, something new, something that couldn't be found in any textbook. Because nobody knew it yet. That's what's happening right now with this interstellar comet, and that's why every new update, every new shift in its trajectory, every new observation matters, because we're not just collecting data, we're watching a story unfold, one measurement at a time.